Hello again, everybody, and welcome to another live stream. My name is Brad Keeler. I'm the director of the Geo-Institute, and you have stumbled upon, or maybe you're here intentionally, GEOSTRATA Extra.
Hello again,
everybody, and welcome to that time again. Every issue of GEOSTRATA, which comes out 6 times a year, we do a deeper dive into one of the articles with one of our authors. In case you don't know anything about the Geo-Institute, yes, we are a technical society. Yes, we have about 12,000 members. And yes, we are part of the American Society of Civil Engineers. And if you like what you see today, and I know that you will because you've all watched live streams before probably and you came back. I guess if it's your first time, you may not know, but I'm telling you now that you're going to enjoy it. You should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. A couple of quick things today. In the United States of America, it is tax day. It is that day when your income taxes are due. So a very kind reminder, if you haven't done them, you probably should by midnight tonight so that you avoid all the bad stuff that comes along with that. The other thing about tax day is it's a great time to think about money. And what better place to put your money than the Geo-Institute Student Programs Fund? Of course, you know we are trying to endow our student programs, and we need every dollar in order to make that happen. We've got some great thank you gifts. Ironically, with Sergei Terzaghi here, we're not going to show you the Carl Terzaghi bobblehead because we sold out of those, but we do have the Ralph Peck bobbleheads available now for a donation of $96 or more. I'm wearing a retro, I guess now, because it's 2023, student competition t-shirt. We have those available as well from 2025 and previous years for a $30 donation, and a bunch of other very cool stuff. So make your contribution to student programs. Last thing before we turn it over to Jeff Dunn, our editor, to introduce our guest today, is that if you desire to read the current issue of GeoStrata, and you should because it's an excellent publication, you should head over to readgeo.com. It is that easy. When you go to that site, you will be faced with this glorious cover of our 25th anniversary magazine, which is the issue that we'll be talking about today. You can go through that very simply, just click around, you go article to article. It's got an amazing page view as well if you prefer to read it that way. However you read it, we do want to say thank you for reading GeoStrata, and thanks to Jim Withiam and Christy Kehoe for all their great work on it over the last quarter century, which is now getting to be kind of a long time. Join us next month as we have a special 25th anniversary celebration of the magazine, Looking Back. You can find registration information for that on our Eventbrite page. Now, the events of today. A very special GeoStrata Extra because it is our 25th anniversary issue. We went big, and you'll recognize the last name of our guest today. You'll probably recognize the first name too because he's a GI member and he's a pretty darn good civil engineer himself. It's Sergei Terzaghi, here to tell you a little bit about his article and about the interview that's going to happen today is GeoStrata editor extraordinaire Jeff Dunn. Jeff, let us know what's going to happen.
Okay, thanks, Brad. Well, today we're going to expand on Sergei's article from the recent issue that Brad just mentioned, titled Terzaghi on Terzaghi. How does Terzaghi's consolidation theory hold up after 100 years of research and application? So I know there's some great points in the article, and Brad just have some time for Sergei to discuss and expand on a number of those that are really critical, I think, to, looking back at how well that theory is still applicable and now that we have more tools for it. To give an introduction to Sergei, he is a principal with A.O. Sullivan and Associates in Katoomba, New South Wales, Australia, which is to the west of Sydney. I can't remember how many kilometers, but maybe 100 or so, something like that, roughly, near the Blue Mountains, a beautiful area of Australia. He's worked throughout much of the entire Pacific Basin during his career, and the range of materials he's worked on has ranged from very young to very old, and in many, many different types of genesis, from sedimentary, windblown, volcanic, metamorphic, and residual. And along with the impact in those differing materials of different minerals on material behavior. I know from experience reading some articles about some of the unusual materials that occur, particularly in that area of the globe. His interests focus on the application of numerical modeling on geotechnical projects, how to make the models reflect reality more, and finding better ways to develop and select appropriate material parameters in those models. And of course, that's key to getting reasonable answers from any model that's applied. So welcome, Sergei, and particularly since I know it's still pretty early there in Australia in the morning. So hopefully I know you're wide awake, so I'm not worried about that. So just a real quick introduction, and then we'll get into some questions and discussion. Consolidation analyses are, of course, widely applied to calculate settlements under load. And Carl Terzaghi's classic one-dimensional theory is literally now 100 years old and still widely used. I was thinking about it, and I imagine as we speak, there are calculations of one-dimensional settlements ongoing all over the world. But we now have computational tools that, of course, weren't available 100 years ago and allow for much more rigorous analysis that enable us to account for factors that aren't accounted for by the simplifying assumptions of one-dimensional theory. However, having powerful tools does not give better results if these tools are improperly understood and used. And that's what Sergei is going to be discussing with us today, expanding on his interesting article, Terzaghi on Terzaghi. So to start off, Sergei, kind of following a little bit in some of the order in your article, you mentioned in it that you were a young fellow, only about a year old in 1963 when Carl Terzaghi passed away. And so obviously your knowledge of him is based on stories about him from family and friends and others. Are there one or two stories that you might like to relate to us, kind of kick things off?
Yeah, sure. Unfortunately, within the family, for many reasons, my aunt, my father, my half-aunt really didn't talk a lot about Carl. So he was, and even my grandmother didn't talk a lot about him. So that was really much a mystery area for me. But it was a lot more interesting when in my younger days of my career. And to be honest, I wish I had the opportunity to repeat the experiences. I had some very good sessions with Ralph Peck when I was visiting the US, and also with Charles Ripley in British Columbia. I had an afternoon with Ralph Peck when we basically, all we did was swap stories. And, you know, there's a classic story of Carl walking through a hydrotunnel penstock and looking at a frog that squished in the cracks of the wall. And then Carl asking, how did that get there? And, you know, the story was, well, it must have got stuck in the penstock when the whole penstock was pressurized. and the crack opened up, and then of course, when they took out the pressure to inspect the tunnel, it got stuck in the crack. And it was really, weren't people thinking about these sort of pressure effects? Nowadays, of course, we think about all of those things, and we go for steel lined tunnels and stuff like that in the penstocks. But back then, that we're still very much learning, I guess, or thinking about other things and not thinking about these sorts of issues. And if you think back to some of the stories I've told in other talks, there are a lot of early events that really shaped Carl's thinking, and that was just reflection of one of those. I think one of the others, which I think probably goes more personal, from Charles Ripley, was whenever Carl would go to British Columbia to look at the various projects he was involved in there, obviously the first stop was in Vancouver, he always booked at the same hotel, and he had to have exactly the same room. And part of Charles' task was making sure that happened. So he was really very certain things had to be done in a very, very particular way, which is kind of interesting. I guess there's the other thing I should mention, because we're going to touch on some of this later on. Carl started off really as, he was trained as an engineer. There wasn't the distinguishing between civil mechanical engineering back then that there is then. However, because of the events of World War I and whatever, he developed an intense dislike for tinkering with anything mechanical. And my father, like all young teenagers, or most young teenage boys, I guess, liked tinkering with old cars, which my grandfather just could not stand. And, for those who are like that, my father had a 12-cylinder motor engine that he loved tinkering with as a teenage boy, which of course drove my grandfather crazy. So some interesting dynamics there, and perceptions on how we do things, because of course Carl loved experimenting in the lab, which we'll talk about maybe later on.
Yeah. Well, those are interesting. Even, if you didn't hear that many stories, but I've found throughout my career hearing little anecdotes like that. I know I heard one story about somebody when they were a grad student in MIT and how they were tasked with driving Carl around Cambridge and how much smoke there would usually be in the car. So that sort of thing. They just add some, really interesting aspects to our understanding of particularly notable folks in our field. You mentioned in your article two of the most important milestones in geotechnical engineering were the development of consolidation theory and then the publication of Erdbau Mechanik, which was published in 1925 and probably the first textbook or book to present soil mechanics as a scientific-based engineering practice. What was it about consolidation theory that makes it, and maybe not the most important, but maybe more important than some other areas of geotechnical practice?
Soil mechanics in various forms has been around for a long time. We think about Rankine theory, and that was developed, I think, in the 1800s. Coulomb theory, maybe even in the 1700s, if I remember my times correctly. Aspects of pile behavior, aspects of bearing capacity, have been around for a long time. Causes of settlement was virtually unknown, and especially consolidation. So the time delay in putting a load on and seeing settlement was completely a black art. People had no basis for assessing it. So presentation of consolidation theory, what it meant, really opened up a whole wide new world for everyone in practicing in the soil mechanics area. They finally had some tools that enabled them to do something instead of hoping. And that's where it's probably one of the most important developments. Of course, with earthbound mechanics, Carl had done a lot of testing and validated things like lateral earth pressure theory and a lot of other stuff. So earthbound mechanics really presented a lot of those findings as well. So I think it was that combination of providing a new set of tools and being able to validate, what he was presenting. And probably, as we're discussing earthbound mechanics, the ICSSMGE conference next year in Vienna is going to celebrate the publication of earthbound mechanics. So following on from Brad, if you're at all interested in those things, you should register and attend.
Yeah, that's interesting. I remember back when I was in graduate school, there was, and I'm not sure what prompted it, but earthbound mechanics had been out of print for quite a while, and then they did another print run, and I remember one of my fellow students bought a copy and was really excited when it was received, but of course it was all in German. He didn't read German, I didn't read German, but it was still a notable thing to have as part of his collection. So you mentioned in the article, and you touched on it just a little bit, about how Carl Terzaghi wasn't maybe a super mechanically oriented guy, but in terms of what his interests were, but he had to develop equipment from interesting sources of materials. I was particularly struck by your mention of cigar boxes that were used as materials in his laboratory experiments. And can you tell us any more about his activities in the library? In the laboratory, I mean? And I think,
if you could...
Yeah, I'll pull up that, see if I can get that. A second here. And push the right button to get to the... There we go.
Yeah, so I've inherited a massive box load of cigar boxes, and I was wondering what was in them. Turns out it's full of slides. So someone was enormously practical with all the cigars. As you mentioned, Carl enveloped himself in a perpetual cloud of smoke, regardless of circumstances. So he went through a lot of cigars. As you can see, there's a lot of slides there, and they're all of his talks and various trips. Hopefully one day I'll make them more accessible. A retirement project. But you can see the nice wooden boxes, good wood, good size for making, for example, a retaining wall in the lab. And you can then use that wood for measuring your lateral earth pressure on the rough surface. We have to remember that his activities in Istanbul were during the World War I, and materials were really scarce. So he had to make use of whatever he could scrounge reuse, but everything else. I haven't heard a lot of his activities in the lab, except he spent a lot of time in the lab measuring, recording, thinking. I think it was quite detrimental to family life because he probably spent more time in the lab than he did at home. But that was, he was in his 40s. He was really driven at that stage to solve some of these problems and come up with a better way of working with soils. Why soils? Well, I guess it was a lifelong passion. So, sorry, it doesn't really answer the question there. But, there's just that spirit of ingenuity and, yeah.
Well, I think that it doesn't maybe answer my direct question there, but it's still enlightening, I think, in terms of some of the limitations at the time in particular. And I know you mentioned some of that in the article, but this, adds a little more to it. And the whole idea of making use of what you can and adapting, using materials or reusing equipment, that sort of thing. I think that's probably continues to this day through research in geotechnical engineering. I know I repurposed a lot of stuff back in graduate school. So the article, kind of taking off from laboratory work, it emphasizes the need, and I think this is something that's very critical, that you really kind of hit the nail on the head, so to speak, but the need for better field and laboratory tests to characterize soil consolidation, and that sorry about that, the fax machine, which I never use, is ringing, but the classic consolidation test using the odometer seems very simple. I mean, having set up and run these tests or had them run, it just seems like a very, very simple test. But it's often run, and I think this is a key thing too, on very poor quality specimens with significant levels of disturbance. I know I've seen some results from consolidation tests where the consolidation curve looked more like part of a circle than anything else, that was endemic of huge levels of disturbance. But from your perspective, what needs to change to support consolidation analyses, particularly, more sophisticated analyses where the parameters become even that much more critical?
Yeah, this is a real interesting one, and we could probably spend 2 or 3 hours discussing this. But a lot that drives my thinking there is something like 90% of the odometers results that I have are valueless, just because of sample disturbance. And this has led to usually severe over-design with its own consequences. In some cases, it's meant that people have missed critical aspects of the problem. There's, and further, in Carl's day, people really didn't care if your calculations were out by 4 inches or 6 inches or even 18 inches, if you think about some of the stories from the early Chicago subway tunnels. They just go around and jack up the buildings after they put in the tunnel through. So people were, so long as you were in the right sort of ballpark, people didn't really care. Of course, today, if you're in the urban environment, if you even talk about moving a building by an inch, you're going to have an army of lawyers baying for your blood. And most highways demand one inch of settlement and abutments in 25 years. Now, we're relying on an odometer test. In principle, it's a very simple test, should be relatively accurate, but because it's very sensitive to disturbance, both during sampling and testing, it's not that reliable. It's not changed in the 100 years since it was brought in. Surely we can do better. I shrug in despair. We've gone from 4 inches, 6 inches, 12 inches of settlement is acceptable to today where 1 inch is not acceptable. And yet we are using the same test that my grandfather used. So we have greater demands and we haven't upped our testing regime. So it's a problem there. I think even though the odometer appears very simple, it's restrained laterally and you're applying the load vertically, what actually happens in the sample is actually very, very complex. And when we're looking at odometer results, we need to think what's happening in the sample. We're changing the stress state very significantly over and above what we're talking about. We plot the result as E log P, with P being the change in sigma 1. But we're not thinking about what's happening laterally as we confine the sample. And then on some samples, that can be very, very significant. And as we're going through an unload-reload cycle, we're actually rotating our stress state. So our sigma 1, as we load the sample, is vertical. Well, if it's a normally consolidated sample, it's vertical. As we unload it, it goes, your sigma 1, your principal stress rotates to be horizontal. And then we reload it and it changes again. And all of those things actually do weird and wonderful things to how the soil behaves. And we don't take that into account. So there's those sorts of issues that we need to be thinking about as we move forward. And also, obviously, how can we get a better sample, larger diameter sample tubes, better thin wall samples, but understanding what's happening in this sample bed is a key element of it. I think the interpretation, our standard E log P curve is very misleading. We need to plot maybe 4 or 5 different types of curves, looking at the energies, looking at EP for some soils. There's a whole range of things that we need to be looking at simultaneously. We also have problems even with E log P, our standard consolidation test. We start off with a confining pressure and we double it every time. Our interpretations are based on that particular interpretation. The problem is, especially when you look at some of the alternative methods of interpreting, we completely miss critical points. Where's the yield curve? If we're dealing with some structured soils, the yield curve isn't related at all to the overburden pressure. It's related to the strength of the material. And we don't know what that is. We can estimate it through other means. But you're going to miss that critical point. I have one classic, quite young material. It was preloaded. We didn't know by how much. And it also had a certain degree of structure. We did our unload reload curve based on the presumptive overburden pressure and completely missed the yield point. And it was rather embarrassing. because we needed to know where that yield point was for the project. So that's some of the things that we need to be thinking about a lot more. I hope to be publishing some papers on some of these aspects in the near future.
No, it sounds like, even with, and correct me if I'm just kind of wrong, but even with using an odometer or classic consolidation test, if we looked at it a different way, we'd get a lot more information than instead of kind of blindly following this doubling of load that we've always done for years and years and so on. So
yeah. I was just going to say, I think we can get a lot more just by, thinking a lot more about what's happening in the sample. I think there is one point, and we'll probably touch on it later on, is we have to remember we're talking about, a 3/4 inch sample, and our real material is 5 feet, 10 feet, 15 feet thick. How does that very tiny sample represent that entire layer?
Yeah, good point. So, and then if we don't get a good sample or specimen from it, I've actually, just real quick thing, I remember one project where I saw the results of a consolidation test that to my mind were virtually worthless, and then I looked at the boring logs, and sure enough, it was a driven sample. So it really was worthless. And when I queried the engineer who had asked for it, I said, "Why'd you bother with the test?" And they said, "Well, we budgeted for it." That's, well, no need to belabor that, but certainly sounds like a fertile area for improvement without a doubt. So
absolutely.
So one of the other things I found very interesting in your article was there was a discussion about the so-called, I guess it's sometimes referred to as the Fillunger affair or something, where one of Carl Terzaghi's colleagues really criticized Professor Fillunger, his 1D consolidation theory. And, in reading this, and I had heard about it, I remember Professor Harry Seed mentioning this in one class back in school. But, when new theories come on, it's not unusual that there's conflict between those that maybe see things a different way. But this one had such a, in the end, a tragic outcome with the suicides of Professor Fillunger and his wife, as you mentioned in the article, and that there was the potential that had this not resolved or ended the way that it did, the three-dimensional consolidation theory might have been developed relatively soon, back in the 1920s or 30s, but that, this and just threw a major delay into that effort. I was wondering, it's like, had that come about back at that time when there, computers still didn't exist, and there were limits on computational capacity, do you think, at least, what do you think would have been different? Maybe, I don't know, sure, speculation, but.
Well, I think there's several aspects to that question. The first one, Carl, despite his dislike for tinkering with mechanical things, was first and foremost a experimentalist, relied very much on the observation of materials and formulated ideas on that, and where he would fit mathematics to it. probably guided by much abler mathematicians than what he was. Professor Fillinger was a theoretical mathematician first and foremost, and experiments were more a way of trying to validate some of the results he had. So very different drivers there. Together, they, could have brought, both sets of thought together to come up with something a lot more powerful. So, that drives some of the things, some of the thinking there. We have to remember back then, we didn't have computers. Things were done by hand, slide rules, log tables, all of that sort of thing. So what people did was they would develop charts, and so that people could come up with a solution. They're very good at developing, I don't want to say true non-dimensional graphs, but something resembling that. So that you solve the equation once, and then people could use them forever. And there's some very good treatises by Froelich and his colleagues, also at Vienna, where they solved the 1D consolidation theory for a whole range of boundary conditions. They would have done exactly the same thing for the 3D theory. And that would have led, I think, to a better understanding of, hey, what drives consolidation? How do we adapt the 1D consolidation theory for the 2D case? We think of Barron's theory and wick drains. What would have happened if that came in 20 years before when he published it? So we would have seen a lot more of those adaptations come in. Yes, it would have been paper, it would have been charts, but, we think about it, I think we get blinded sometimes with, hey, we just plug this into the computer and out spits an answer. People did build massive embankments on very soft soils with very simple tools. And they would have used the tools available to them in creative ways.
No, I think that's a real good point. It's like if the theory had been there, the appreciation of that alternative would have progressed in a totally different way. So, even though you didn't have finite elements or something back then, or computers to run it, analyze that sort of thing, but still just an appreciation of it. So, which that transitions real well into the next area of discussion or questions. You mentioned in your article some of the key simplifications of one-dimensional theory. They're a nice, succinct list, and that these assumptions, I think you commented that in certain cases they're okay. They're pretty good applicability, but not all cases when 1D theory is applied, but it's used routinely and on many projects. And you mentioned that if it's a complex project or a demanding project, the validity of the simplifications may come into question, and there may be aspects that point that they're in question. And one you emphasized, and I think we'll talk about this, or you'll mention this now, is the importance of shear strains and what they do to pore pressures, and not just the vertical one-dimensional loading. And one-dimensional theory doesn't account for that impact of shear strains. So how does, from your perspective, how would you or another practitioner recognize the need to go to a more rigorous theory and not just do what they normally do, apply one-dimensional theory and use some more analysis tools available?
If you could bring up the slides, we'll go through some of the things. But, in principle, the 1D equation reflects a settling layer of infinite expanse in all directions. So if we're moving away from that, we're going to have problems. And, there could be a geometrical issue. So this is from one of my very early, well, maybe mid-career projects, which really actually started bringing out some of the shortcomings that we're discussing. Yes, there are issues of unusual materials. Yes, there are issues of phase changes because we're talking about a geothermal fluid, but fundamentally it's still a consolidation because we're talking about changes in pore pressure inducing settlement. Now you can see here we have a lot of very irregular layers. They're different shapes. A lot of people are trying to solve it using multiple 1D approximations. However, you can see how all of the settlements are concentrated along the slope there, which is not explained by pressure changes or changes in material. It's explained that as the layer, that pink wedge, well, actually, no, it's actually the green wedge underneath it consolidates. We're inducing shear strains in the material, which then induces concentrated settlement there. 1D just doesn't capture that sort of change in behavior. And the variable thickness, we're getting different settlements in different areas, and it's generating other effects as well, which may lead to additional movements and deformations. So geometric effects is one thing. If we can move on to the next slide. External loadings is another one. Now, this is a much more complicated case. On the right-hand side, we can probably use 1D theory quite adequately because we've got a layer. The blue layers are your soft layers. They represent sort of an infinite expanse. However, on the left-hand side, at the edge of the gray embankment, we're going to modify the edge, add a new load, and in fact, another track there. And so we're going to be adding loading there. But you're also adding a lot of modifying the shear strains through there. So your 1D theory doesn't actually capture that. It's also an unloading, reloading problem. So you've got multiple problems occurring through there. And how do you address and the constraints of a 1D problem, your unload, reload, and the change in shear that's occurring? So whenever you're getting these sorts of changes and stress changes in loading, you need to look at something that's a bit more sophisticated. And what's also really important is that you don't apply your own thinking, because the stress states on the edge there, they're not really what we think about in terms of load spreads or anything else. They're concentrated in very different ways. Now, of course, if you're being really want to make fun, you also have the impact of your dynamic train loadings and how that densifies the materials at depth. But that's almost a different discussion altogether. But it is real and did play a major role here. And if we could have the next slide. You know, I couldn't find my slides on here, but just some things. 1D theory, if you look at your CV is relatively constant for well-behaved, normally consolidated soils. So your MV changes decreases as the soil becomes stiffer as you go through consolidation. K decreases as well. They compensate each other. So CV remains relatively constant. But what happens if MV and K are no longer coupled? Your CV changes fairly significantly during your consolidation process, and consolidation theory no longer works. In some cases, it's okay. In other cases, it's not so okay. We also, it's driven by water. So you have to think about what's going to happen if you have some other fluid there. And possibly, what if it's something like saline water? What happens there? Because you're getting your changes in salinity. Is that going to change your behavior? There are examples where, we introduced a change in the salinity and it changed our consolidation process partway through the project too, which was embarrassing for everyone. Interestingly, I've had a couple of projects now on Holocene materials, like the Younger Bay Muds in San Francisco, similar age, where there's almost no primary settlement. We could demonstrate that by the fact that the pore pressures basically dissipated in 24 hours. Minimal settlements, yet 2 or 3 years later, we had, a foot of settlement. To me, that represents a complete new area that needs to be more carefully examined. And it's certainly not captured by any form of 1D theory that I'm aware of. So that's some of the shortcomings and some of the areas where we can be looking, I think.
Well, yeah, that last kind of transitions into the next topic very, very nicely, of what we can put in the box of secondary compression, and which was not understood back when one-dimensional theory was developed. And I think you commented on it. I'd have to agree with. I don't think it's very well understood now. It's maybe it's something that people just, it's like, well, I'm not going to worry about that. But in some cases, you just mentioned, it's much bigger than primary consolidation might be under certain loading. You mentioned having had project experiences too, that particularly with the wide variety of materials you worked with in your career that showed varying mechanisms of secondary compression compared to, the traditional description that appears in textbooks or, in part of soil behavior or something. What do you have an example or two of some of those varying materials?
Yeah, so I've had the joys, if you can call it that, of working with again, the Holocene clay materials, so they are typically 5,000 to 10,000 years old, usually deposited in a marine or estuarine, some kind of freshwater environment. Each one, the 3 sites in Australia, each one of them had completely different secondary compression behavior. One site behaved almost in a beautifully viscoplastic behavior, very well behaved by the soft soil creep model in Plaxis. In fact, it was almost a poster child for that soil model, so long as you calibrated it correctly. We have another site where, let's just say it's not well described by any existing soil model. It's like the soil behavior got locked at its deposition pressure, and what you had to do, and it got frozen there, and if you broke it, it would drop very, very quickly down to your normally consolidated line. If you accelerated the process through installation of wick drains, which of course broke it, you'd get very large settlements. But once you hit that line, you got almost no creep. Everything up until then, if you were loading it without wicks, without anything else, would manifest itself as a form of creep. So very different behavior through there. We had another site which kind of had aspects of both behaviors. So it was you had to be really careful with how you load it, how you treated it. And, the traditional concepts about your previous overburden pressure, had no creep up until then, and after that you could have creep and primary settlements, just did not apply. Yes, I'm still trying to grapple with how do I deal with that material, but again, very, very different behaviors, and there isn't the framework to adequately deal with those. Well, there are. You just add enough load to make sure, and leave it there long enough to make sure you get everything out of the system. But that's cost and time and money.
Yeah, and I can think of a few clients that would send you out of a room if you brought that up to them. So,
yeah, exactly.
I can't afford that, or what, are you crazy, or something like that.
Yeah.
So, yeah. So, getting around to our last topic of discussion, you noted that in the 1950s, BIOT provided a coherent 3D consolidation theory that really holds up, and has been applied and forms the basis with all the tools we now have for computational efficiency to do 3-dimensional analyses and potentially generate the inputs that we need to try and do that relatively accurately. But you mentioned that these tools that are available to us, that are out there, we have such a wide range that cover many, many areas of soil mechanics and behavior, but they're not always selected properly. And of course, as we've touched on more than once, good input data is not always collected. The quality of samples and the parameters and so on. But you touched on that well in the article, but do you have any other comments on that further?
Yeah, look, we we've touched on multiple aspects of the issues here. One is, of course, the input data. How good is the input data? How good do we understand the geology? How good do we understand how the site developed? Without understanding those, you can have, a very nice 3D model, but it's meaningless because it's not capturing the essential behaviors that we need to see on site. That goes into selection also, not just of the soil parameters, it's also the soil models. Like I said, in the previous case, some sites you've got soil models that capture the behaviors well. Other sites not so well, and you need to appreciate which ones are which. It's not just go automatically, oh, well, I'm going to use this program, I'm going to use this soil model because that's what we did last time. You need to match up those sorts of characteristics. Going back to the Fillinger affair, there's an element here of how much of what you're putting into your model is reality. That's the Carl side of things. How much of it is reality that are we reflecting? How much of this is just mathematics? And Carl has a quote, which I'll probably misquote here, but it's along the lines that mathematicians should be locked in golden cages and fed problems judiciously. And at times when we're relying on these very sophisticated models, because that's what they are really very sophisticated, I do wonder whether we should be locking ourselves in the golden cage, because we're relying more on the mathematics rather than on practical observation as to what's there. And I'm sure when you're mentoring your young staff, you will do a calculation on the back of an envelope in about 2 minutes, and your poor graduate spends the next week setting up their computer models and getting an answer that's way off base after a week. And this is this reflection of we have to temper whatever we put into the computer with a bit of sanity, a bit of common sense, really understand what it's telling us. To me, these 3D models, they're just one tool in the toolbox. And many problems require simultaneous application of 2 or 3 or 4 different tools just to make sure that we get a sensible answer that we can advise people. And of course, this gets a lot more complicated, demanding, if we're looking at any form of reservoirs where we've got local geology that might be influencing things. We might be getting phase changes depending on what the reservoir is. So yeah, there's a lot of things to look at and consider. And you always have to ask yourself, what am I not considering?
Yeah. Just real quick before we wrap up, want to remind our viewers, if you have any questions, go ahead and post them in the chat hopefully quickly if any pop up. I think, Sergei, you're noting, talking about particularly younger staff who are so savvy now with the use of, numerical stuff and that sort of thing. But in compute, they don't even call them computers, I've heard. It's just, my tablet, my laptop, whatever. But I remember one project where we did some numerical modeling, and the person who did it was very, very well qualified. But the answers they wanted to report, and it wasn't a settlement, but it was horizontal movement. They wanted to report into the 100th of an inch. And I sat down with them and said, well, we're not going to do that. I think, like we touched on a little bit, you know, from the legal perspective, that could be very, very difficult. And I remember a response was, well, but the model, that's what the model tells me, you know, and it's like, well, yeah, no, I understand that, you know, and it's like you can set the, you know, the output parameters for so many decimal places and so on. But, you know, the input we have is not that good. If you were to change, you know, this parameter or that parameter, what would the answer, how much would the answer change? And, you know, we're still up against that. So we have powerful tools, but we have to, I think you have to still maintain sight of the real world, the picture. Like, and I think your emphasis on the geology, the depositional environment, and that sort of thing is how critical and how important those are to actually understanding problems and to looking at the answers we get from any number of tools, be they simple, applying one-dimensional analyses, hopefully with some decent test data, or if they're very, very sophisticated. And,
yeah.
You know, so.
You know, I keep reminding people of Duncan's paper, you know, talking about the parameters of the Younger Bay muds. And, you know, it's a very well documented material. Yet we still don't know basic parameters like C sub C to better than plus or minus 30%. You know, and then, you know, we're asking people, oh, you've got to calculate to 1 inch. Well, you've got a 30-foot thick layer. You're not going to calculate to 1 inch when you're plus or minus 30%.
Yeah.
Sort of thing.
And how many thousands and thousands of tests have been run on
exactly
Bay mud? Yeah. Food for thought. So, well, anything else, Sergei, you'd like to add in closing comments or anything?
Well, you know, I think I just really want to emphasize consolidation theory is only one part of the problem. It's understanding the geology, it's understanding the formation, how the formation was formed. Well, I want to say depositional environment because most often it is. It's not always just the straight depositional environment that impacts things. You know, if you're in the floodplain, you're going to have these real thin, high permeable zones in between your thicker zones. You're not going to test those thin zones. What is the impact? Well, on one site, I had, from odometers, I had a CV of 4 meters squared per year, very slow. In practice, it was more like 70 meters squared per year. Very, very big difference. What is the influence? You know, really common in Australia, we have a crust. That crust is formed by desiccation. That gets buried. How does that influence our results? And I don't think we actually understand what that means. Certainly, it throws out all ideas of OCR out the window because there is no previous over-consolidation. Yet it behaves like it was over-consolidated, but doesn't have the stress rotations or anything else. So it's really, you know, as we look at problems, particularly in a different environment and as people get more and more demanding, we need to be more sensitive to these issues. I think that's really the major thing there.
Yeah. Well, I think that brings things to a real good close. Is, yeah, we have these tools, but we got to pay attention to the details, which Absolutely. I'm not saying anything new there, I know. So, yep. Well, thank you, Sergei. That was a very interesting session. I see, Brad, you've joined us back. So thank you to Sergei Terzaghi for his GEOSTRATA Extra session. And Brad, I'll turn it back over to you.
But I do want to take this opportunity to ask you a question, Sergei. And you guys kind of chipped away at this, but Jeff, I don't think you asked this one directly. This isn't something that's limited to just the geotech discipline either. I think there are a lot of people out there in the world who would look at something, theory by the leader of the field, and would say, well, this is the greatest individual that our field has ever seen. We should just leave that alone. Why are we questioning it? Why are we trying to add to it? What's your response to that, Sergei? Why should we look at maybe not just this, but other theory? You named a few right off the top, whether it was Coulomb, or I'm trying to think of the other one you pulled out. But why even revisit these things?
The simple answer is our understanding advances. So today we have tools, we have understanding that Carl didn't have back then. So his thinking, while it was revolutionary at the time, is really outdated. If we were to start afresh with what we understand now, we would have something different, a lot more comprehensive, and maybe addresses some of the shortcomings that we are seeing. Carl himself say, you shouldn't just take someone's word. You need to challenge. You need to validate for yourself what's there. Otherwise, you just become stagnant and almost doomed to failure because you're not advancing the field. He recognized very carefully that he was just representing a snapshot in time, and it's arguably the best that we could have done at that time. But I think he'd be very disappointed in us that we haven't done anything better than SPTs, to be quite blunt. Especially when we have very nice tools like your seismic CPTUs and seismic dilatometers. We should be looking at using those a lot more. They're more reliable, they're more scientific. Of course, I'll be the first to say beware of correlations, because they're very heavily dependent on the local materials. But they're more reliable tools than your old-fashioned SPT. So that doesn't, what I'm saying doesn't apply just to geomechanics. It applies right across almost every discipline. When we start saying, oh, so-and-so said something, it's just reflecting that we've become stagnant, complacent, and not willing to challenge the boundaries.
That is a great answer. And it really does reflect, I love talking to you and I love listening to you because you take that really simple thing and it becomes so thoughtful. I love that. And I want to say thanks especially for doing this. All of our viewers, Sergei lives in Australia. It's currently 5:10 in the morning where he lives, and he got up to do this for us. So a massive thank you for appearing on this episode of GeoStrata Extra. Of course, I have to say thanks to Jeff as well for doing the interview. A fantastic job as always. And a big thanks to our viewers for being here with us. We wouldn't be able to do these live streams. I guess we could, but they'd be kind of boring if nobody showed up to watch us. So thanks everybody for hanging out with us for the last hour and a little bit. We really do appreciate it. Only message here at the end is our next live stream is coming up 1 week from today. It will be in the same time slot on the 22nd. It's the 4th episode of GI Books Rock, where we feature a publication and we talk to the author for an extended interview, we'll call it. We'll have Craig Davis, Southern California's own Craig Davis, next week, talking about his publication, Infrastructure System Resilience. Sergei, Jeff, thank you guys so much for doing this and for doing a great job today. We really appreciate it. Producer today was Aurora Flieger. Great job as always, and we will see everybody very soon